Hello, and thank you for the opportunity to talk to you today. Dmitrii and I will share our recent work on shielding Linux application containers in an untrusted cloud. Recently, these untrusted clouds have seen a surge in applications computing on sensitive and private data. And when sensitive and private data is involved, the risks of their exposure is even higher. Before I start with the presentation, it's important to note this legal disclaimer. This talk is about the data protection gap that exists in untrusted clouds. Sensitive data is encrypted while it is in transit and at rest, but it is not while it is in use. As a result, sensitive data may be exposed to the cloud's infrastructure system software while it is in use. This creates a strong desire to compute on encrypted data. This new form of computing is called confidential computing. It protects your data against data confidentiality and integrity violations while protecting against replays. It mainly relies on encryption of the main memory. This form of computing relies on trusted execution environments, or TEEs. A TEE typically is implemented in hardware, in this case shown here in the CPU. The hardware is trusted to isolate the TEE from the remaining system. It does so by mapping the TEE's memory in a secure portion, hence denying access from any non-TEE execution. In addition, the CPU attests the state of the TEE to third parties that ask for an attestation. This allows an external verifier to provision secrets to the TEE. Today's TEE of choice is Intel's SGX, software guard extensions. But before looking at SGX, let's consider the attack surface of a regular application. The attack surface typically includes the entire system, software, OS, and hardware. Intel SGX changes this attack surface. It is implemented as an ISA extension that allows an application to be split into an untrusted component and a trusted enclave. These trusted enclaves are shown here as green squares. After the split, the hardware ensures that neither the untrusted component of the application or any of the system software can access the trusted enclave's memory. In the SGX model, an untrusted application builds the trusted enclave given its initial state, including some well-defined entry points. Before provisioning secrets to such an untrusted enclave, a third party verifies an attestation evidence that is produced by the hardware that typically includes the memory fingerprint as well as the defined entry points. This allows the third party to now trust the enclave and ship the private keys, for example. Application into an untrusted component and a trusted enclave ensures a very small TCB and strong security guarantees. It increases the effort to build and maintain such a split. In an untrusted cloud environment, though, we're using SGX not necessarily to split the application, but rather to shield against the cloud's system software from gaining access to our valuable sensitive data of our application. This results in a design where the entire application runs inside a trusted enclave, shielded against access from the system software. Unfortunately, the restrictive programming model of Intel SGX denies system calls from an application. To overcome this limitation either requires modifying the application or using a LibraryOS. A LibraryOS provides a generic Linux system call API to the application while securely translating these system calls that the application does through the SGX boundary into the host OS. The LibraryOS we've been involved with is called Graphene. It has been adopted to Intel SGX, providing the interface to run unmodified Linux applications within Intel SGX enclaves. Let me introduce Dmitrii, who is one of the core maintainers of Graphene. He will provide the details on Graphene before we apply Graphene to application containers.
Thank you, Anjo, for the kind introduction. As already mentioned, Graphene is a library operating system that allows to run an unmodified application inside an SGX enclave. Graphene is an open source, community supported project, and it is currently in the process of transitioning from a research proof of concept to production ready software. Graphene serves as a minimal bootloader and an emulation layer sitting between the application and the underlying host OS. You can think of Graphene as a minimal re-implementation of a Linux kernel which strives to resolve most application requests in the form of system calls and open source files in user space, and occasionally resorting to host OS provided resources like network I/O, file system I/O, thread scheduling, process creation, and so on. Graphene additionally implements extensive checks on system call arguments and return values, helping to protect against maliciously crafted values. And by design, Graphene consists of two layers: the stateful LibraryOS layer that intercepts system call requests from the user application, verifies inputs, processes these requests, verifies outputs, updates the internal state of Graphene, and then gives the results back to the application. And the stateless platform adaptation layer, or PAL for short, which is invoked by the LibOS layer only when the host OS must be involved in request processing. As you can see, Graphene currently supports more than 300 system calls, maps them to around 40 PAL ABI functions, and PAL uses around 50 actual system calls to communicate with the host OS. Now, this picture shows the non-SGX version of Graphene. Let us move to the SGX version. When Graphene is run in Intel SGX mode, it loads itself and the application inside of the SGX enclave. The major parts of Graphene move inside the enclave, in particular the LibOS layer and most of the PAL. However, PAL is now divided into two separate binaries, the untrusted PAL and the trusted one. The untrusted PAL is used to load and initialize the SGX enclave in the wrapper process and to issue system calls to the host OS on behalf of the enclave. It also serves as glue code to enter enclave mode and then exit it. Similarly to other layers, the interface between the trusted PAL executing inside the enclave and the untrusted PAL executing outside is kept minimal, with around 40 so-called SGX outcalls or OCalls in total. Graphene takes additional precautions to harden this boundary between the trusted enclave and the untrusted environment. As typical in security-critical environments, the application running inside Graphene and an SGX enclave must be accompanied by a security manifest. In fact, it is this security manifest and not the application binary that is given to Graphene as input. This security manifest is a plain text file in a simple format. Here is a small example. First, the manifest must specify the actual executable to load and run, in this case, the Python-free executable. Next, the manifest may override the required environment variables. The manifest should also specify a subset of hostOS directories to be mounted, so that only they are visible to the enclavized application, possibly under a different name, as shown in this example. Here, the glibc libraries are silently replaced with Graphene patched glibc libraries. Next, the manifest contains some SGX architecture-specific variables like the maximum enclave size and the maximum number of simultaneous enclave threads. These are the limitations of SGX version 1. Finally, this example shows how files to be consumed by the enclave must be marked as trusted. In this case, Graphene calculates the secure hashes during build time, appends these hashes to the manifest, and then during runtime, Graphene will verify that the files were not modified. There are several more manifest options to Graphene to enable additional functionality. So this manifest is the single most important file when porting applications to Graphene and Intel SGX. Ultimately, the security and correct functioning of the application depends on how its manifest file is written. A very important aspect of any trusted execution environment is attestation. How can a remote user verify that her application actually runs in a correct, up-to-date TE and that the code that runs inside the TE is the actual user application? Moreover, how can the remote user provision any secret inputs to the application remotely and in a secure fashion, and then get the results of execution also in a secure fashion back? Intel SGX, similarly to other TEs, provides a way for the SGX enclave to attest itself to the remote user. This way, the user gains trust in the SGX enclave running in an untrusted environment, ship the application code and data, and be sure that the results were executed inside a genuine SGX enclave. We will show a complete, though slightly simplified flow of remote attestation. Every SGX-enabled processor contains a key burnt into its fuses. The processor uses this secret key to encrypt all memory traffic leaving the CPU package. So all manufactured SGX processors are listed in the web service maintained by Intel called Intel Provisioning Certification Service. At deployment time, the new SGX machine is supposed to be registered with this service. There is a special SGX enclave called Provisioning Certification Enclave developed by Intel. This enclave is used to connect to the Intel Provisioning Certification Service, send the ID of the SGX processor and other identifying information, and receive the normal X509 certificate for this machine signed with the Intel public key. This certificate is used to prove that the SGX processor is genuine and up-to-date. Now the user wants to run an enclavized application with a security-sensitive workload. The user possesses a trusted machine, not needed to be SGX enabled, and the first thing the user must do before outsourcing her secure workload is to contact the Intel Provisioning Certification Service to retrieve the required certificates, certificate revocation lists, and other SGX identifying information. This information can be cached in a local database, so that the user doesn't have to establish internet connection to the provisioning certification service every time she runs a workload on a remote, untrusted machine. The user also installs the quote verification software that runs all the required checks during remote attestation. Now the user ships the application binary and the Graphene runtime to the remote, untrusted machine. Note that no sensitive inputs are shipped to the remote machine just yet. So the remote machine starts Graphene, which starts the application binary inside of the SGX enclave. The user also starts a secret provider application on her own machine. This application will connect to the remote machine, establish a secure communication channel, verify that the remote machine is a genuine SGX-enabled machine and that the application and Graphene run in a genuine SGX enclave, and after that release secret inputs to this remote machine. So secret inputs are represented as a keyring on this diagram. Note that since the user shipped Graphene and binary to a remote machine, the user knows their corresponding expected measurements. Intel SGX software infrastructure has another special enclave called Quoting Enclave. This enclave with a reference implementation written by Intel is used to create a special structure called the SGX quote. This SGX quote contains all the information about the particular enclave, including its hardware-generated measurements. You can think of the SGX quote as a second-level certificate that proves the authenticity of the enclave. Graphene contains two libraries that transparently add remote attestation to the application. The ArrayTLS library augments normal SSL TLS sessions with an SGX-specific handshake callback. The secret provisioning library builds on top of ArrayTLS and runs before the application. First, the secret provisioning library instructs ArrayTLS to collect all SGX-related certificates and create a normal X509 certificate chain out of them. Then, a secret provisioning library establishes a secure TLS channel with the user's machine. During TLS handshake, ArrayTLS library installs a special verification callback that receives the certificate chain with three certificates: the leaf ArrayTLS certificate, the second-level SGX quote identifying the enclave, and the top-level certificate identifying the SGX platform. Since the three certificates in the chain contain all SGX-related information, the user compares the retrieved measurements against the expected ones and decides whether to trust the remote enclave or not. If the user-side verification finishes successfully, the user then gains trust in the remote enclave, and now using the same secret provisioning library, sends the secret inputs into the SGX enclave. After this point, the secrets are injected in the application, and the application finally starts its execution. The same secure channel may be reused to securely send application's results back to the user. Graphene also implements the feature of protected files. Since the user application runs on an untrusted machine, all input files, as well as produced output files, must be at least integrity protected. And if user files contain sensitive information, they must also be encrypted. With a protected file system implemented in Graphene, all required files to run the workload are created by the user on her trusted premises first. The files are then encrypted with a symmetric key. After that, the files may be shipped to the untrusted machine together with the application binary and Graphene. After the SGX enclave is created, Graphene needs to obtain the key used to encrypt the files. As explained previously, this key provisioning can be accomplished via secret provisioning with remote attestation. So once the key is securely provisioned inside the enclave, protected FS subsystem of Graphene uses this key to decrypt the input files and run the workload. After the enclave is finished with a secure computation, the application typically produces an output file. This file is also transparently encrypted by the protected FS with the same encryption key. Finally, the output file may be moved to the remote user, where it will be decrypted. Graphene implements protected files as transparently encrypted and integrity-protected files. The specific files or whole directories to be treated as protected must be specified in the manifest. The encryption format used in the protected FS implementation is borrowed from a similar feature of Intel SGX SDK. We would like to stress that Graphene is an open source project maintained by a dedicated community with contributors from several companies and universities. We successfully enabled several widely used applications in Graphene across several domains and hope to support more use cases as we grow. And at this point, I would like to give the mic back to Anjo.
Thank you for the introduction of Graphene. We will now switch gears and look at how to use Graphene for application containers. Containers have become the de facto deployment model for the cloud besides virtual machines. They provide a small memory footprint and a fast startup time. We cannot directly apply Graphene to container frameworks. We first have to overcome two obstacles. The first one is that Graphene does not provide an interface to create images or containers. Second, while providing handcrafted manifests, as Dmitrii explained, is possible, it's a huge burden on the application developer or engineer. To encourage the usage of our container integration, we have to simplify the manifest drastically. For this purpose, we have created Graphene Shielded Containers, or GSC. It takes as an input a regular Docker image with an application and its dependencies, and optionally a minimal application manifest detailing its memory and parallelism requirements. These two are given to GSC to build a graphenized Docker image. This image includes the application, the Graphene runtime, and a generated manifest file based on the user's inputs, as well as some configurations of the Docker image. All SGX applications have to be signed by the developer's key. GSC signs applications in the runtime and the manifest in a second step to ensure that the user's signing key is never part of the persistent image. The signed image can then be started via a regular Docker run command, which starts the Graphene runtime. The runtime loads the manifest, which then starts building the enclave according to the manifest specification and starts running the application. On the previous slide, I simplified the manifest file generation substantially. Let me explain how we semi-automatically generate a manifest file from a Docker image. We base our automation on the observation that a container defines the minimal runtime environment of an application. This means that files included inside the container are dependent libraries, required script files, static inputs, or a particular configuration argument. Using this observation, we can generate a majority of the fields that constitute a manifest file. I've listed here only a few examples, and we'll go through them one by one. The executable and its arguments are specified typically inside the Docker's image configuration via an entry point or a command. We repurpose these configuration fields to generate the executable and its arguments in the manifest file. In addition, each manifest file includes a description of the file system layout. Since we consider the entire file system of the container to be a dependency of the application that runs, we simply set the file system to the root of the container. Lastly, each application will open files, in particular any dependent shared libraries. Without specifying any dependencies as trusted files, Graphene will simply deny access to these files. This is to ensure that any open file has a pre-recorded SHA-256 hash and ensuring its integrity and hence that nobody tampered with it. We overestimate this set of files to be all files in the container. Using GSC, we have developed 3 deployment scenarios. In the first scenario, the client builds the graphenized Docker image on-premise and then ships it to the CSP's registry. Afterwards, he can rely on Docker's run command infrastructure to create graphenized Docker images as usual. In the second scenario, the client uploads the application Docker image. Subsequently, she graphenizes the image via a CSP's infrastructure interface, and again afterwards may use a Docker run command to deploy a graphenized Docker image. In this third scenario, a client uploads his image again to the cloud's registry, but instead the image is not translated via an API call to the CSP. The client directly runs the image, specifying a runtime. This runtime uses GSC to translate a regular image into a graphenized Docker image on the fly. This approach lowers the required changes in the client software to a minimal change to run the correct runtime. Before I show you a demo of GSC, I'd like to provide an end-to-end use case that makes use of attestation, protectfs, and Graphene shielded containers. In this use case, we use GSC to package and deploy Graphene with an application, in particular a PyTorch object detection. We assume the model, the input, and the output of the PyTorch object detection to be secrets. Therefore, the runtime has to first obtain a provisioned key to access the model and the input. We do so by generating an attestation and sending it to the verifier. After validating the attestation, the verifier releases the provisioned key to the runtime. We then use the provisioned keys to access the model and the input from the protected file system. This allows Graphene to transparently decrypt the inputs without a single application change. PyTorch then detects the objects within the input and generates an output or a decision. The decision is then stored securely within the encrypted file system. This use case combined various techniques to protect the confidentiality and integrity of the model, the input data, such as images, and the inferred output from the model. So now I will show a demonstration of Graphene shielded containers. We are graphenizing the public Dockerup image of Python. For the purpose of that, we're specifying the GSC build command. In this demonstration, we're using insecure arguments, but technically you can specify trusted arguments as well. We're graphenizing the Python image and we're specifying a Python manifest file. In this manifest, we're adding a single line to allow file creations, which is required for PyCache to work. We're then following the GSC Docker build process. It first builds Graphene and then copies over into the application image the required runtime arguments. We are then copying over the Docker run command that specifies the required SGX devices. We're specifying the image, gsc-python, which is the graphenized version, in addition to a Python arguments. Again, those are insecure. And we're basically printing Hello Linux Security Summit from an enclave. We then start the container. We specify, or we see that the token was generated, the fingerprint of the enclave and the fingerprint of the signer as shown, and then Graphene is started with a manifest that was produced by GSC and the insecure arguments again. You can use trusted arguments if that's required for your production environment. Now we should wait a couple of seconds and see that Hello Linux Security Summit was successfully printed. I'd like to highlight the current and future directions of Graphene. Graphene had its first major release last year, and we are currently in the process of finishing our next release. This release includes remote attestation, exit lists, system calls, protected FS, Graphene shielded containers, and secure multiprocess support using encrypted IPC. In addition, Graphene has been accepted to the Confidential Computing Consortium, which is part of the Linux Foundation. Thank you very much. I would like to invite you to ask questions, and I've put up a couple of links in case you want to know more about Graphene. Thank you.